God morgon Oslo. Tack för att dere valgte vår presentation. Välkommen till Pattern-Based C#. So today Stefan and I are going to take you on a whirlwind tour through C# language patterns.
So is that going to the direction of pattern matching, where we can, for example, write an expression such as this, which checks if all these properties are fulfilled and if this expression does return true? We would end up with printing the result to the console.
Well, pattern matching is a great topic, but not the one we'll cover today, because it is about checking an expression for specific characteristics, whereas we're going to be talking about compiler-recognized patterns. So, language features that don't rely on interfaces or inheritance, but rather on a type's shape.
So is this something like the dynamic keyword, where we can basically foreach anything?
Kind of, but dynamic does allow you to bypass type checks at compile time, whereas we're going to be talking about type-safe patterns of the C# compiler. So yes, indeed, we'll be able to make our own type for eachable, but in a compile time checked fashion.
I see, because this does compile, however, at runtime with dynamic we now get a exception at runtime because we cannot foreach an integer. So are you saying that we could foreach our talk type, even though it may not implement the IEnumerable interface?
Absolutely, we can and we will. But before we go into that, we've got a little something for you to make this talk a little bit fun and interactive. So please, everybody take out your phones right now. You wouldn't want to miss out on those amazing prizes, because we've got a little quiz for you. And all those questions are directly based on what we'll show you today. So if you don't know the answers straight away, don't worry, just follow along and you'll learn them. All right, I guess it's time to introduce myself. Hello, my name is Eva. I work for a company called Radency. We build cloud-based talent acquisition software that helps companies around the world hire smarter and faster. And I'm a little bit new to all of this because I've actually only been coding for about 3 years, which was right around the time that I joined Stefan on his live stream. But the one thing that really helped me learn throughout the years was to have a look behind the scenes at what's going on there. And that's exactly what I'll be doing with you today. So I'll be the one always peeking under the hood to show you how the compiler actually thinks, what is it looking for, what patterns does it recognize, and how can you teach it new tricks. So whether you're new to C# or have been around since while was controversial, I hope this talk helps you see the language in a new way and gives you the confidence to dig deeper.
And I will be the one implementing these patterns. And while at it, shifting left all these ducks over to my side. Hello, I'm Stefan Pölz. I'm a Microsoft MVP, a JetBrains community contributor, and a co-host of the .NET meetup in Vienna. I work at Century, where we build libraries for, various ecosystems, also of course .NET, that helps you find problems in your applications sooner and more precisely. Also recently, we started to embrace and explore language patterns, so at the end we're also going to have a real-life example.
Awesome. And both of us mentioned our live stream. So it's called To Code or Not to Code. And it's our bi-weekly excuse to get together, code together, learn together, laugh together. And this talk actually came out of one of our episodes, where we built a source generator that lets you deconstruct any type. Now, what does that mean? All right. Yep. Thank you so much. All right, so what have we got here? We've got our talk class here. We've got 3 properties, title, conference, and start. Up here, we create an instance, a new instance, and this is where it gets interesting. So this is the deconstruction syntax. So on the left-hand side, we declare a tuple of variables, and on the right-hand side, we've got the instance of our class. So far, so good. This also compiles, but you might have noticed this little attribute here. So that's from our source generator, and that's what makes this possible. So if I get rid of it, you should see, yep, there they are, some squiggly lines appearing right here. The compiler does not know what to do. So let me just pop it back and also run it, just to see if it actually works. I mean, yeah, it does. Amazing. So we've got actually the correct content printed to the console. And fun fact, a record class does this out of the box. And as chance would have it, I do actually have a little record class just down here for you prepared. And we create an instance up there. Yeah, all right, okay, you can see it. Let me just pop this over there, and let's run this again. So you can see it compiles straight away, and indeed we get the correct output. So now, as promised, let's have a look behind the scenes. I'm gonna open my IL view here, and you can see I'm at low-level C# there. And if I scroll to the side, you can see that we call deconstruct right here. And that's actually what was missing beforehand when we had the squiggly lines. Because when the compiler sees the deconstruction syntax, it looks for a method called deconstruct, exactly deconstruct. And it also checks that this method has the corresponding out characters. So in order to make your to enable the deconstruct pattern for your type, though, this is the shape that you need to fulfill. All right, so let me close this window. And I don't want to use a record. I just want to use a normal, regular class. And maybe I also don't want to use this source generator that some shady Austrians built on a live stream. So I'm also going to get rid of this attribute here. Now we've got squiggly lines appearing, and this is where you come in, Stefan. So can you manually enable deconstruct for our type? Because if you get the shape just right, the compiler would think, if it looks like a duck, swims like a duck, and quacks like a duck, it probably is a little deconstruction duck.
It's time to tear this down. All right. So what the source generator did under the hood, it was creating an extension method with our talk type as a receiver. So you can enable this via an extension method, but also as an instance method. If you have both, the compiler usually prefers instance methods. So I'll now enhance our talk type with this deconstruct method. Currently we see we have the error, and the compiler already gives us a hint that no deconstruct method with 3 out parameters was found on this type. So let's supply just that. Let's provide a public, could also be internal in our case. It needs to be accessible of where the compiler is eventually then calling it. Since it's in the same assembly, we could also make it internal, but we keep everything public for today. Now let's call this exactly deconstruct with exactly that spelling. And we need to have 3 out arguments, exactly the string, and datetime offset that we are deconstructing into. So let's turn this into 3 out parameters. And we see the error up there has already disappeared. Now we just need to get the implementation detail right. And we just assign from the properties to this out parameters, because the out keyword in C# enforces the method that's implementing them to definitely assign them. And now we have absolutely no errors anymore and just enabled the deconstruction for our type. Now we're using 3 parameters. Deconstructions can also be overloaded by amount of parameters, not by type, but by amount. So for example, we also want to have a string deconstruction. Now the compiler gives me the hint, there is no deconstruct method with 2 out parameters. So let's overload our deconstruct. Let's get rid of the datetime, so we only have the 2 strings. And again, it compiles. Now we can deconstruct into a string or deconstruct into a string datetime offset.
Amazing, and that's our first pattern enabled. So let's have another example that's super satisfying because everyone's used this one before. And it's collection initialization. So I'm going to write a list of int. I'm just going to call it list because I'm creative today. And let's have new. And maybe let's pop in, let's start with 0, 1, 2, 3, 4. Okay, that looks pretty good. Just to make it a bit more visible, let's for each this and print it to the console. All right, simple as that. Let's run this just to make sure, you know, I don't get that wrong. Okay, good, basics are right. Now, I'm not going to focus too much on the for each or the console write line just now. But I am going to be focusing on this very first line here, so the initialization. Because if I open my trusty IL view, I can see what the compiler makes of it. So, oops, let me just get rid of this. Okay. So we create a list here, and then we can see that we call add once for each item in the initializer. And that looks like a pattern to me. So if we write our own add method, could we then initialize our own type in the same way? I don't know. Let's see. I'm just going to duplicate this line here. I'm just going to call this hour, just to make it a bit more distinguishable, and also going to fill it with 5, 6, 7, 8, 9. Oops. And I'm not going to use list. I'm going to use our list. OK. Let me create this. Perfect. So this does not compile, and actually error message already says cannot resolve symbol add. So Stefan, can you make our list quack like a proper collection initializer?
Yes, I can. Not only am I going to add the add method, also adding another duck to my collection. So we saw that we do indeed need the add method. This can be void. We call it exactly add. We have a generic list, so we want to have a generic set of items here initialized. And, well, this doesn't compile just yet. We now have another error that says we cannot use the collection initializer because it doesn't implement the IEnumerable or the IEnumerable of T interface. So now for collection initialization to enable, the type also needs to be a collection-like, so it needs to be enumerable. So let's also implement, in our case, the generic IEnumerable interface. Let's implement the missing members, both the generic and the non-generic version. And we see it already compiles, but at one time it wouldn't work. So as implementation detail, I'll just add an underlying list of T, and we'll just forward to that list. So a bit of a delegating type, more or less. Just adding to the list. And also, when we get the enumerator, return the one from the list as well. So now this not only compiles, but also should run exactly like before. But now we can collection initialize our list with 5, 6, 7, 8, and 9. Amazing.
And you can also initialize dictionaries, but they take 2 values. So can we also try that with our add?
That's right. I'm just going to add some spacing in between to make this a little bit more visible. What we could have, per item we add, also explicitly set curly braces around. These are optional. When we have adds with more than one item, like a dictionary, that's a key value pair, so we want to add a key and a value, then we need those braces so that we can do a comma in between. And in this case, I will add just another 6. Now we see the singular item add works, but the one with 2 does not work because we only have an add method with 1 parameter, but it's invoked with 2. So just again, let's provide another overload that now does not take 1 item, but 2 items. The implementation detail, I'll just ignore it, but compilation should be fine, unless, what am I doing wrong? I am not quite certain where my mistake is, perhaps somewhere curly brace, but if I wouldn't have made a syntax error, now what we would see is that for the singular items, we would call the add that takes 1 argument, and for the one with 2 here, we call the add with 2 methods, and we could extend this with 3, any amount of items.
Awesome. All right, but yeah, so we've got some red here.
Oh, there is a hidden 6 up there that messed up everything.
All right. But I can see some green squiggly lines here as well. Or do you want to? Yeah, perfect. Okay, so the IDE is actually having some suggestions for us as well, namely to use collection expression. So let's oblige it. I'm just going to use it here. And it also suggests it for our list. Amazing. Okay, let's do it. Looks a lot cleaner, no more new, no more curly braces. Perfect. But also, under the hood, something's changed as well. I'm just going to build this real quick and then open the IL view. And you can see we no longer call add, but instead we create a stack allocated span and use it to fill the list in one go. That's really, really good for performance, super cool. I love it. That's great. But if I scroll down, even though it looks the same on the left-hand side, actually under the hood, our list still does the old add thing here, and that could potentially grow the underlying array of the underlying list. So it's not great for performance. I don't like that. So Stefan, could you also add this span magic to our list, please?
Yes, I love spans. So we see that as a fallback, the compiler will be using the add methods if available for the collection expression. Also, the Roslyn compiler knows the list type intrinsically. It has very good knowledge, so it generates super special codes for it. For other lists or collection types that the compiler is not intrinsically aware of, something like the immutable array, there is a pattern that we need to fulfill in order to opt in to be collection initializable. And if we take a peek at immutable array, it does come, since recent versions, with the collection builder attribute. And this is now teaching the compiler how to collection initialize our types. So we're going to add to our list the collection builder attribute. This takes 2 arguments. One is the type where this create method is being found that the compiler calls. This must be on a non-generic type, so we also need to add a non-generic type to our compilation. And also, we add the name of the method that the compiler should invoke. It's common practice to call this one create. So let us create this public static class our list. This needs to be non-generic. And we will add the create method. Now this needs to be a static method, and it returns an instance of our list that or of the type of the collection that we want to initialize. In our case, our list of T. So create now becomes generic, and the parameter type is a read-only span. And since we have a generic list, we will do a read-only span of T. And compiler is already working. Now let's get the implementation detail right, so we actually see something on the screen. So let's return a new instance of our list. Let's pass in the read-only span, and let's provide a suitable constructor, where, as an implementation detail, we will just do an add range. And if we run that now, we should get now the same collection initialized behavior with our type. And if we take a peek under the hood, there should no longer be any add methods called. It should be a one-shot creation via exactly the method on the type that we declared, our list.create. And the compiler will do some inline arrays. I think they're part of the assembly, so super, super optimized from the invocation point of view.
Amazing. And this collection builder attribute also reminded me of another episode that we had on our live stream where we delved a little bit deeper into this topic. So if you're interested, definitely go and have a peek. It's on YouTube. But okay, so we've initialized our collection. Now let's access some individual items. So I'm going to do a little console write line. I'm just going to access the first item. And that's going to be simple, because it already suggested, I'm going to go in with index 0, because we all know that's always going to be the first item. Okay, amazing. But so what about the last item? So, okay, right now I can see that it would be index 4, but, I might not, see the list a couple of lines above declared. So I always want this to work, even if I don't see what's going on. So I'm going to use _1. So that's the from end syntax. So _1 would be the last item, _2 would be second to last, and so on and so forth. All right, I'm going to run this. Oh, yeah, I'm going to run this and then show you. So it prints out the right stuff, and so it works, right? We can all see it, which is interesting because this caret is actually of type index. And that's interesting because list does not have an index-based indexer. It only has an int-based indexer. But it works. Everybody saw it, right? So let's have a look at what's going on under the hood. All right, so we can see that, so index 0 remained the same, okay, we expected that, and the _1 was actually rewritten to be count -1, right? So why -1? Because that was after the caret. If it was _2, it would be -2, and so on and so forth, and that makes sense, because we have, how many? 5 items in there. -1 is 4, if we go in with index 4, that's the last item. If we had _0, we would go in with index 5, and that would obviously be an index out of range exception. All right. I mean, you already know the drill by now. I want this to also work for our list type, and squiggly lines appear. That means it's time for Stefan and another duck.
Let's get into implicit indexing. Well, I could write a explicit indexer, a public T returning an indexer is written with the T keyword, which takes, for example, now then the index. I could have this an index, system.index-based indexer. And we don't have any compiler errors anymore, but this is explicit indexing. We want to get into the implicit indexing, which is based on an int here. So as an implementation detail, so that also works at runtime, let's just index into our list. But now the from end semantics is not enabled yet, because for from end semantics to work, we need to know the count of the list. So we need to go from the end. And in order to do that, we can provide another property, namely a count property. So this is now making our collection countable. We see the exception is gone. As an implementation detail, let's also just forward to the count of our list. And now our list should work exactly the same as the BCL's list, and we can get the first and the last item implicitly. Alternatively, to the count, the compiler is also searching for a length. The difference is usually when you have a collection that can grow or shrink, like a list, you have a count, which is representing the current size. If you have a fixed size collection, like a span or an array, you usually have the term length. It cannot change during its lifetime. And if both are available, you see the compiler is highlighting the length. Length is prepared, but you shouldn't have both. This is confusing. You can't have a collection that's both not growing, but also growing. And one thing, what I noticed, so backtick _1 is the last element. If we were to do _0, that actually does work at compile time, but at runtime, we would now index into the count, which is one index higher than is available, and we run into a good old argument out of range exception.
Amazing. Cool. So let's slice things up. All right. I'm going to get rid of the console write lines here, because you know that worked. And I'm going to, in the foreach, I'm now going to go back in with the normal list, and I'm going to use a range. So I'm not going to print all the items. I'm going to go in with 1, 3, so that should print 1 and 2, because this is the type range, and range has an inclusive start and an exclusive end. So we want to start at index 1, so we don't want 0, and we want to end at index 3 exclusively. So no 3, no 4, just 1 and 2. All right, let's see if this also works in practice. It does indeed. Good news for me. And all right, let's have a look in our trusty IL view. And so we can see that the list calls slice here. And I went in with range 1, 3. We see 2 arguments here, 1 and 2. Why is it 1 and 2? Well, because with slice, you have a start for the first argument and a length for the second argument. So yes, we want to start at index 1, and we want 1 and 2, so length 2. Easy as that. But we've just spoken a little bit about the caret, so I wanted to have the same behavior now with caret. So I'm going to go in with caret 2, because we said before caret 1 is the last item, caret 2 second to last item. I'm going to run this. We get 1 and 2 again. Amazing. And when we look under the hood, we see our slice method again, but this time we also have the caret syntax. So we still start at 1, because the start is the same, and then we go in with count -2. So we already said before the 2 comes from the caret, so caret 1 was -1, caret 2 -2, but we have another -1 here. And that's obviously because we don't start from the very, very beginning, because we also don't want to print the 0, right? So if we calculate the length, we also need to take from the back and from the front to get 1 and 2. So yeah, we again basically get the same thing. So with 2 arguments, start at 1 and length of 2. Okie dokes. And does this work with our list out of the box? No, it doesn't, squiggly lines. So Stefan, come to the rescue, please.
Not only do I enjoy slices of pizza, I also enjoy slicing of collections. So we could do, again, make it now explicit by providing an indexer that takes a range. And it should return a collection, but yeah, the compiler would not select the range. It doesn't work because it's not foreachable, but the range pattern now would be fulfilled. But we want to do implicit slicing, where we don't explicitly call the slice method, but we just provide it. We already have the indexer, we already have the length and or the count available that is required to calculate the length for the slice. So all we need to do is provide the slice method. It's a public now collection returning. We return another instance of our list of t, and we call this method exactly slice, and it takes 2 arguments, the start and the length of slicing. Now we see it compiles already. Let's also get it working at runtime. Let's create a new our list of t and provide it with a slice of our underlying list. So again, just delegating to the already working implementation from the BCL. Now we just need to provide yet another constructor overload that takes a list of t. Let's just assign it. Now everything should compile, and we should indeed get the same behavior, cutting off from our 5 through 9 list, the first and last element, and we get 6 and 7.
Amazing. So we've created our collection, we've indexed into it. Now let's focus a little bit on the foreach as kind of teaser at the beginning. Just gonna pop list back. Oh, actually I'm gonna pop our back. So just get rid of this range here. Because we've seen this work throughout the talk, right? But we also noticed that obviously we are implementing IEnumerable of t, so we kind of expect this to work. But for the foreach pattern, the interface is actually not required. So LINQ heavily relies on it, but we're not linking today, so we can actually get rid of this. Now something doesn't compile down here. I'm also just going to delete this, so no interface anymore. But when I run this, well, it still works. So we must have already implemented the pattern without really knowing it. And some of you might have spotted this already, because if I scroll down a little bit, is we still have this get enumerator method here, and that actually fulfills the pattern already. So when we look in the IL view in a minute, keep an eye out for this, because I want to show you something else as well. And for that, I'm going to go back now to the list. I'm just going to build this. And open the window here. All right, and we can already see the getEnumerator method right there. So this is what enabled the pattern. And we can also see that it returns an enumerator that has a move next method that returns a bool. And while this is true, oh, I actually drew over this now, but you can see it accesses the current property of the enumerator as well. In the finally block, we also call dispose, so that's definitely something that you totally should do, but it's not necessary for the pattern. For the pattern, we actually only need a parameterless getEnumerator method that returns a type that has a bool returning move next, and a current property that has at least a get accessor, because we need to access it. All right, now let's go back to our list, because if I scroll down, we are using the IEnumerator of T here. And I was wondering, could we write our own enumerator?
I believe we can. So instead of using the already existing systems collection.generic IEnumerator, which fulfills the pattern, which has the current property, as well as the bool returning move next method, we'll just implement the same for our list. We call this now our enumerator. We just typed it doesn't exist. I'll add it as a nested type. I want to make it a ref struct because I want to use span in there. And let's call this our enumerator. Let's add those two methods that now, well, for methods and properties that this one needs. So we need to return a t, the current item, as well as have a move next, a bool returning move next method Awaitable. Move next is moving the state machine forward, where the current then after we have moved to the next item can be accessed. Let's return an instance of our enumerator, and we see we are still compiling, so for each is still happy. Let's also get the implementation detail right. So in our enumerator, let's add a span of t that will hold the data and also some state where the state machine then moves forward. Let's let it be an index. And let's start at -1, indicating that the enumerator has not been started yet. Let's provide a constructor that takes now on the underlying list. And let's extract the span out of that list. Now we can get the implementation detail right. So when we move next, we want to move the index forward. Let's increment the index. And if we are still in bound of our underlying span, then we return true, meaning there is another item to be get via current. If we come to the end, we return false, which means the iterator has reached its end and current should no longer be accessed in the while loop, and the while loop actually exited. So let's now also just return the current item. We don't see any compiler errors, and if I didn't forget anything, it should just be foreachable the same without implementing the IEnumerable interface and by providing our own IEnumerator method. And the return type is significant here, because this is now the type that is available in the foreach loop. We could, for example, change this to return by ref, which now enables the ref keyword in our foreach loop.
Awesome. And I mentioned before that dispose is not necessary for the pattern. We've proven it isn't, but it is definitely good to have. So could we add this as well?
So let's make our enumerator IDisposable, and let's implement the IDispose method. And just to see that it is actually invoked implicitly by the compiler, let's say dispose here. Let's run it, and we should get 5 through 9, and at the end, a dispose.
Okay, but wait a second, because we are working with a ref struct, right?
Yeah.
And that was only able to implement interfaces since C#13, right? So what if we were working with an older version without the interface?
Let's travel back in time. Let's go back to language version 12, where we couldn't have interfaces in ref structs. Now the compiler yells at us and says, yeah, please upgrade to C#13 because C#12 doesn't support interfaces on ref structs, but can it still be disposable without the interface? It appears to be.
Awesome. Looks like a pattern.
It does indeed look like a pattern. So now I'm wondering if it works for every type. Let's do an our disposable type using our disposable. Bit of a typo, but it doesn't matter. And let's find out if for other types this is also a pattern. Let's create a public class, our disposable, and call the public void dispose method. For class, it's not a pattern. We must implement the iDisposable interface.
Yep.
For regular struct, it is not a pattern. We must implement the iDisposable interface. Only for ref structs, because ref structs were introduced in C# 7.2, and with C# 8 we can now have the disposable pattern on ref structs, because they only can implement interfaces in C# 12.
Cool. All right, we've gone from building collections to navigating them. Are you ready for some async and await magic next?
Ooh, async state.
I hope so. So I'm going to make this for each async. I'm going to add await, and I'm going to have it call a method called getItems async. So down here, I'm just going to declare static async I async enumerable of int returning method getItems async. And in here, let's have a for loop with an upper 5. That suits me actually pretty well. Let's await task dot delay. Okay, that's not enough. Let's have 1,000 milliseconds. Okay, and then let's also yield return I. I think you left my ref in here. Trying to trip me up, huh? All right, okay, let's try and run this. Fingers crossed. Any more traps?
I don't think so.
No, okay, perfect. So now all the items are getting printed to the console with a slight delay. Wonderful. Now let's see what makes this tick under the hood. Okay, so we're in async land, so this looks a little bit different, but we can see a few familiar faces. For example, in synchronous land, if you remember, we had the getEnumerator method, and here I can see getAsync enumerator. So that looks pretty good. It's like a clue already. And we also had moveNext, and here we have moveNext async. Wonderful. Familiar faces. And if I scroll down a little bit as well, you can also see that we also still have the current property, which is synchronous, because properties can't be async, of course. And these shapes aren't accidental. They're actually the async equivalent of the foreach pattern. And with that knowledge, we should be able to await foreach our type as well. So, good luck.
Thank you. All right, I don't want to destroy the existing synchronous enumeration, so I'll just create another method, and we call this the getAsync enumerator. And we will return an async enumerator. I will also duplicate our synchronous enumerator and rename this to our async enumerator. Now, async and ref structs don't go too well. Ref structs must be on the stack, where with asynchrony you may end up on the heap. So let's create a good old class. We can't use a span anymore, so let's fall back to an array. Let's rename this into our async enumerator. And let's fulfill the pattern. We need to be async, so this is moveNext async. Now this can't return a bool, but it must return something awaitable of bool, such as a value task. Which means now we can make this method async and do the same await task.delay in here to delay it by, let's say, 500 milliseconds per iteration. And the property current is just synchronous as it used to be. We don't have any compiler errors anymore, and now we should be able to asynchronously foreach our list as well.
Amazing. And with the synchronous for each, we had dispose, so can we now also add dispose async?
Right, I'm now going ahead and call this dispose async, and also return a value task. Here we just return value task. Let's call this async dispose. And even without implementing, I could implement the async disposable interface. And it will be working. Dispose async is called. But we can, for async disposal, for any type, that means classes, web structs, and regular structs, dispose async is a pattern. So even without the interface on our enumerator, we can asynchronously for each our list with now 5 to 9 with a 500 millisecond delay, and at the end we get disposed. Async disposed.
Perfect. And we can not only await for each, we can actually await anything. And that's what I'm going to show you right now. So for that, I'm going to be dramatic and delete everything that we've just built, just to have like a clean slate. And I'm going to have a console.writeLine. All right, let me put in before. And I'm going to have date time. Oh, no, I can't see what I'm typing. Offset now. OK, perfect. And let me duplicate this. Let's have after. And in between, let me await task delay, and let's have, OK, time span from minutes. OK, well, let's have from seconds. OK, guys. And let's have 2 seconds. OK, that should look good. Let's run this. We should have 2 date times with 2 seconds apart. Wait. Is that right? Let me run this again. Yes, okay, perfect. Good. Amazing. And let's have a look what's going on under the hood. Okay. Whew, loads of async stuff, but let's focus on the things that we do recognize from the code that we wrote on the left-hand side. For example, I can spot the before here, so we've got before there. I can see the after from here. And I can also spot the task delay. I can spot it right here. And we can see that on this we call get a waiter. And that returns an awaiter that has an is completed property. And if it's not completed, we can see that we record the state here. And then the async method builder calls await unsafe uncompleted. And you can spot it just on the right-hand side here that we pass our awaiter in as a ref. So that means our awaiter must implement INotify completion or ICritical notify completion. OK, and then we return out of this. And right at the end, we also call get result. And that's where you might return a value or rethrow an exception, things like that. And whew, that's a lot of red on a screen, but I really just want to draw your attention to get awaiter is completed, the fact that we pass it here as a ref, and the get result down there. And with this pattern, you should be able to await anything. For example, we could await time span. Wow. Enjoy.
Thanks for handing me my favorite duck, the .NET duck. Since async and wait is, I'm a bit of a aficionado of that. All right, so we need to await time span. Time span is a type of the BCL. We cannot extend it. We cannot add an instance method to it. So just as with for each, with collection initialization, and with many patterns, we can also provide an extension method with the type that we want to enable this feature for as a receiver. So let's do exactly that. Let's create an extensions class here. And let's provide a static, I do void for now, a method that is called getWaiter. That is the name that must match. And since it's static, we need to also pass the receiver type where we say this time span. So we're now expanding the time span for the awaiter. And we need to return something awaitable. I know that the task awaiter is fulfilling the pattern that you just showed. So let's return a task.delay with our time span, and let's get the awaiter of it. And the pattern is fulfilled, and now we should be able to just await a time span where the compiler is now calling into get awaiter, and we have the same 2 seconds cooldown behavior.
Yeah, but isn't this cheating? Because we're still using the built-in task awaiter. Can we write our own awaiter?
Yes, we can. So let's write our awaiter. Let's create a new instance of our awaiter, and let's pass in the time span to it. Let's have the type, public sealed class, our awaiter type. Now our awaiter type needs to have the property is completed. So for the state machine to know, bool returning is completed. For the state machine to know if the task is already completed at that time, we don't need any asynchrony and can just continue. Now we need to implement either the INotify completion interface or the ICritical notify completion interface, where the ICritical notify completion interface is implementing INotify completion as well. The difference is how the state machine flows execution context and or synchronization context. I always forget these two. They don't matter too much in .NET Core these days anymore. So let's provide both of these methods. And the last one was the get result method. We also need a constructor here for this to compile, and we still are awaitable here. Now let's, so for evidence that we can also show, let's also provide some implementation detail. I'll do again some delegating implementation, where we just move what we had before into this type, which then the compiler is calling. And let's just forward our properties that the compiler is matching to the already existing implementation, because getting an awaiter right is not the easiest task.
Fair enough.
On completed with the continuation, same for the unsafe on completed, which comes through the ICritical notify completion interface. And also let's get the result where we would rethrow exceptions if any occur during our asynchronous execution. And we now have our very own our awaiter type, fulfilling the pattern being awaitable by the state machine.
Amazing. And I saw that your get result is void, but what if we want to return something? So maybe I can put, let's have a time span, let's call it delay. And let me try and print this delay to the console. Yeah, can we do that?
Yes. I really need to earn this tag. So if we have now the await, the compiler will give us a hint of, well, we cannot convert void to system time span. And this is where the result, the get result comes in. So instead of void, we will return now the thing that we want to return out of the await, in our case a time span. Let's capture it here into a field and just return it. And now we basically, in our state machine, can capture this value, and when it has completed, flow it back out and print it to the console. And now after 2 seconds, we should also get 2 seconds printed. And here they are.
Amazing. Wow, okay, so that was quite a few patterns, and also now is the time to press submit on your quiz. Remember that from the very beginning. You should now be able to answer all of the questions and then press submit. You don't want to miss out on the awesome prizes that we have for you, so do that. And while you're doing that, we do have a few minutes for some bonus content, because by now you'll be like us and you'll be seeing patterns everywhere. For example, I mean, we've seen them also during the talk, the async method builder.
Yes, when we take a peek at the async state machine, we see that an async task builder is used and a lot of methods called on there, such as, at the time of await, this await unsafe on completed. And all these methods have a very specific shape, so we could provide for the async state machine our own async method builder. We're not going into too much detail, just showing that it works. We have our more patterns type, one async, where we have built a method that is now taking the async method builder attribute, where we specify now our custom async awaiter builder. And this is just a struct, no interface implemented. And when we run through it, we will see the pattern. So we need to have a static create method, a start method, a set state machine method, these unsafe uncompleted and await unsafe uncompleted, where now our interface INotify completion or critical notify completion comes in. And for the end, set result, set exception, and then we get the task out of there. And when we run this code, now we should see the very same behavior, but the compiler no longer binds to the existing async method builder, but to our async method builder. So when we take a peek under the hood, we will now see that the state machine is now using our custom async task method builder. And it works because all the other methods are still called the very same. And this is, for example, how value task works. Whenever we have a value task needs its own async method builder. And when we go to the task property of it, there it is, it will return task. It will return this value task. So you can, in your own async method builder, you can here now return your own awaitable type to also be able to return your own awaitable type out of any async method.
All right. And another pattern that you also might have spotted during our presentation was the interpolated string handler, because we had a lot of $signs and interpolated strings, and that's a pattern as well.
Exactly. So we have the dollars here, and then the compiler per default is using the default interpolated string handler. And we can replace this default interpolated string handler with our own interpolated string handler. I'm now going to another solution, the real-life example that I've promised. So at Sentry, we are right now building a logging, and whenever an exception occurs, we attach these logs to your errors. And I'm experimenting here with a method that is now taking a custom interpolated string handler, which has the shape of, it needs to have this attribute, and has append literal and append formatted methods. The append formatted can be generic, or you have it as fixed types as well. When we execute this code, we should, well, run into this exception and then also print this message, where now under the hood, this interpolated string is actually transferred to usage of the interpolated string handler. When we take a peek at the generated code, we will see now our custom interpolated string handler is used. We can also have a bool out argument to that. Basically, if you have a logger and you want to enable or disable a logger, and if the logger is disabled, you don't do any work with the interpolated string handler. So nothing is happening in the case of, oops, sorry, now I went to the exception. Let's move on. So in the case of the logger being disabled, no work is actually being done. Only when the logger is enabled, now these append literal and append formatted methods are called. And we see the pattern. So for every literal string in our interpolated string, we call append literal. And for every interpolation holes that we have with the braces, we call append formatted. And with that, we can now build our own logging provider. That is, if we refresh that, we should now see this exception with some logs attached. There it is. And we should also have structured logging enabled. So here is our log, and we can see that we extracted all this information, this append literal and append formatted, out of the string, where we even passed the date time, and we understand that we had a string, but also a date time as append literals as parameters to our interpolated string.
Awesome. And obviously the language is always evolving, so there's actually a new pattern coming up with C#14, namely dictionary expressions. So that should be fun. But actually, not everything is an extendable pattern like the ones we showed you today. For example, the new lock type. So that's a pattern, but you can create your own custom type, fulfill the shape perfectly, and it will still not work. It only works for system.threading.lock. All right.
I believe we have some time for questions now. Did we leave any questions unanswered? Also, if there is some questions that we cannot answer right away, then with this QR code, we can see. We can see
all of our socials
yes.
and links, and also to our stream. So yeah, if you like this kind of content, do stop by at our stream. We do it bi-weekly, and it's really a lot of fun, and it's always good to see familiar faces there as well. All right.
Are there some open questions? Yes, please.
In the last example, we showed the custom string interpolation handler.
Mm-hmm.
Can you store the intermediate result in a variable and then send that in?
Mm-hmm. So basically, how does the intermediate string handler, a little bit more detail, work under the hood, and can we extract values out of there? Let me briefly show that. So all we take here is basically, well, an interpolated string. And how this works is we now have as this argument, well, we don't take a string, but our interpolated string handler. And we can also pass arguments to this interpolated string handler. So we can, if we have just an empty string, this means this instance where we're currently on the sentry structured logger is now passed to the interpolated string handler. And if we take a look at the constructor of the interpolated string handler, we will actually see the literal length, which is the accumulation of all the literal characters in our strings, and also how many formatted holes that we need to fill. And what we do is also providing the caller argument expression here to extract the original template that this interpolated string handler was called with. And since the interpolated string handler is just an instance of any type, usually you want to do a struct so that you can have it on the heap, on the stack, and avoid additional stack allocations. And in there you can have your fields, store your data, so everything that the compiler is invoking via append literal and or append formatted, but append formatted can be generic as well. You can store in these fields, and then later on, when your method is called, the compiler has already filled those append literals and append formatted, and then you can extract it out of there. If this answers the question.
Yeah.
Cool. Some more questions? Then we do have a couple of minutes left. I wanna share with you one big revelation that I had while we prepared for that talk, and of course I'm going into a benchmark. So if we show the benchmark here, we initialize a list between 0 and 10, and then we assign this list, well, to an instance of list, but also implicitly convert it to an IEnumerable, because a list is implementing the IEnumerable. Now we have two sum methods where we we iterate in the same instance, but once we had a static type list of t, and once we had a static type IEnumerable of t. And if we jump into the benchmark, we will see a bit of a difference where when we iterate through the list of t enumerator, we are faster and also have 0 allocations. But when we use the interface, we actually, well, a little bit slower and also have some heap allocations, which is caused by boxing. This is because if we decompile that, we will see that when we get the enumerator for each from the list, we actually get the list enumerator, and this is a struct type. So when we enumerate the list, we get a struct type and 0 allocation and as fast as possible. But if we cast it to the interface that it implements, now we actually box this struct-based enumerator to this interface, have some boxing allocations, and then also some virtual calls. Well, the virtual calls, the runtime is pretty well aware of how to strip them away, but we do have a bit of performance benefit. So the static type, the takeaway is here that the static type that the compiler sees is quite relevant in order for the pattern then to manifest and which methods then are called from your type.
Awesome. Yeah, so unfortunately, you do seem to have a few technical difficulties with our quiz, so I suppose we'll have to announce it in the Slack channel. Maybe.
Perhaps, since you had a question, would you like to come forward and we may have a prize for you? And maybe if somebody would like to come forward, maybe we do a, what's that, rock, paper, scissors to have the prize. I'm afraid we had some difficulties with the form. Please apologize.
It's live. Okay, but no, thank you guys so much for attending our session. It's been an absolute pleasure to have you here. And I guess there's only one thing left to say.
Tack för att dere deltog på vår presentation. Hygg dere på resten av konferensen. Tack för oss.